As John said, my name is J. Paul Reed. I'm not going to read all the things on this slide. The most important thing on this slide is my Twitter handle, which is easy to remember. It's J. Paul Reed. So if I say something during this talk and you have questions or you want to chat about something, you can always tweet me. You can DM me, but oftentimes the conversation is better with other folks on the Twitter sphere. So go ahead and feel free to contact me there. So what are we going to be talking about today? We're going to talk a little bit about the R words. We're going to talk about the stories we tell, and we're going to talk about the root cause of stress and incidents, and then we're going to tie it all together. So let's get in there with what these R words that we talk about. So this talk was called The Halo of Resilience Engineering, and before we can really talk about any of that or improving incident outcomes using resilience engineering, it's good to set the stage for that. So let's start defining a little bit of what resilience engineering and some of the other R words that we throw around, what those words mean. I kind of, this is the same book cover as the previous slide, but sometimes there's a lot of confusion. I love this cover because I'm like, I don't know what that's supposed to be of. Is like waves of light or what's going on there? So we're going to try to understand that a little bit. So these are the words, the R's that we talk a lot about: robustness, reliability, resilience, resiliency, rebound. We're going to talk about all of these, and we're going to start with resiliency. I laugh. I hear resiliency a lot. I laugh because when you put this into Google, you will get, did you mean resilience? But also I was looking up at sort of the etymology of the word, and it was interesting, but I'd say most usage authorities consider resiliency a needless variant. And you can see that red line on the graph. It's usage of the two words over time. Resilience is sort of the preferred word. I thought it was interesting that they said resiliency is used primarily in academic contents, but in the safety sciences, which is the background that I sort of have, it's called resilience engineering. So I want to walk through the 4 R's that we talked about on the previous slide with an example. And I'm going to, I have to admit, I stole this example from Alex Ellman, who's _PKill on Twitter. And we'll see the tweet that he made about it. But we're going to talk about the different R properties of a system that is an intersection. And I'll make some analogies to the systems we work in as well. But this is going to set the stage for what we mean when we mean resilience engineering and what we don't mean. So the first one to talk about is robustness. And I'm going to give you the academic definition. System X, a system that is robust is system X that has property Y that is robust in sense Z to perturbation W. Lots of letters there. But what does that mean? In the example of the intersection, incandescent light bulbs are more robust, or sorry, LED light bulbs are more robust than incandescent light bulbs because each unit is sort of self-contained. So if you lose one of those filaments, the entire light doesn't go down. They're also like more, you can impact them, right? There's no light in there that might break. They're made out of plastic, right? In software, an example of this might be languages that have memory safety guarantees. So like Java and Rust instead of C or C++. So they're robust in the sort of memory safety context, but not necessarily in broader other context. So the key point here that's important is disturbances to this particular system are really well modeled, and we're solving a specific situation that we think is going to be poked in a certain way. In this case, the light, right, the filament, right? And so we predicted the ways that we've seen those fail, and then we want to make it robust in that context. The next R word, reliability. So these are patterns that support consistent operations or service levels. And so in this example, this light, stoplight is reliable because there are multiple packs of lighting filaments showing the light. Now, interestingly, of course, it's important that they're all synced together and showing the same light, so we designed for that. There's also another way that they're actually reliable is the fact that they have a standard design and there's multiple lights in each pack. So if one of the green lights of the 3 goes down, you can still sort of infer that the intersection is okay to proceed through. So it's interesting that they're kind of reliable in a couple different ways. In the computer space, cloud, or more accurately, multi-region cloud is an example of where we get reliability. In software, developing on multiple platforms, we may see an issue on Linux with a piece of cross-platform software where on Linux it crashes, but it doesn't crash on Windows, even though it's still the same bug, right? So the environment is slightly different, and we can get reliability out of having a piece of software that runs on 2 operating systems. So the key point here is the disturbances are well modeled, but the properties around it are patterns and practices that we put into the system when we design it or improve it. The third of the 4 R words, rebound. So the ability to deal with crisis, situation dependent on the structures that have been developed before the chaos arrives. And so in the intersection example, right, we've got the pavement paint, right? That's sort of the bound of where we expect folks to walk. But if lots of people are crossing the street, they may actually go outside of those bounds. You'll see there's a car sitting kind of in one of the crosswalks. You're not supposed to do that. But if you want to clear the intersection, there's buffer in there for that to happen. Hopefully there aren't people trying to walk while they're doing that. The other example I gave, this is actually a picture of an intersection during the California wildfires, right? When towns had to be evacuated, the road basically got reused in different ways, and they changed the direction, so all of the traffic was going one way. We also actually saw this a lot in COVID, how we started using different systems for purposes that they had never really been used like that before. But that buffer existed, and so that we were able to sort of have the system stretch a little bit. In software example, a CI/CD pipeline is a great one. If you have an emergency deployment that you need to do, if you've gone ahead and modeled everything in your CI/CD deployment pipeline, you're less likely to forget certain mistakes that you might forget sort of under pressure. And so you can use that pipeline as sort of capacity if you need to do an emergency deployment, or maybe with the Log4j many emergency deployments. I know we dealt with that at Netflix, the Log4j issue, as a lot of you did. So the key point here, though, is rebound already exists in the system, and it's informed by previous experience, previous maybe chaos that we then add some buffer and elasticity to that system. Finally, resilience in the intersection context. Great example, and this is the example that Alex brought up. There was a power outage in New York, and it was somebody going into the intersection and directing traffic out in the middle of the intersection. It wasn't a police officer or a traffic person, an MTA person. It was just the guy who was keeping traffic going and making sure that cars making left turns weren't plowing over people in the intersection trying to cross via the crosswalk. And so his original tweet, LED arrays instead of bulbs, is an example of robustness, but that New Yorker is an example of resilience. So why is this important? Why is this distinction important? Well, resilience isn't something that you have. It's something that you do. And so this is important. We often hear a safety science people say resilience is a verb. It's a thing you do, right? So this is important to the resilience engineering community and the safety science community, because you'll often hear us talking about the word socio-technical systems, right? The social aspect, the people aspect of a system that make it better. And that's what we're going to talk further about in the rest of the talk. One of the things I'll point out is I hear a lot of times people say after an incident, oh, we made our system more resilient. And the answer is you probably actually didn't, at least not in the way you think. You probably made it more reliable. You may have made it more robust. You may have added rebound to the system. But unless you're talking about things that the organization can do and the people are doing differently, you're not really adding resilience as it's defined here. All right. Next, we're going to talk about the stories that we tell, because we're talking about people. Let's talk about the stories. So I want to go into the underpinnings of the theory. It's a little digression. It's short, I promise, about storytelling. So this is Jay Bloom. He's getting a PhD in design. He works for Red Hat. And he is studying his PhD, how can we intentionally address ourselves towards futures? So what does that actually mean? He's looking at, like, how do we design cities for 300-year or 1,000-year lifespans? What are the questions that we would want to think about now if we were trying to do that? And then not only what are the questions, but how would we go about doing that? So he brings up this idea, something called the time span of discretion. The slide might be hard to see, but basically you can see complexity and scope of responsibility. And it goes from knowledge worker, people like you and I, through director, VP, and C-suite. The thing that might be hard to see on there is each of those, there's some boxes there that sort of overlap. And they're talking about the time span of discretion. So the first box is 2 weeks. That's the knowledge worker. The second box is 3 months. And the last box is like 5 years. But you'll notice that, like, the C-suite and the director, those boxes really don't overlap. The 3-month box and the 5-year box, they only overlap like a little tiny bit. And we'll talk about why that's important in a moment. Second part of the theory here that's important is when we tell stories about the future, there's kind of a lens that we all look through it, right? And so there's this idea that there are things that are probably going to happen in the future, right? They are probable outcomes. And of course, you can extend this model to plausible outcomes, right? So things that are likely to happen, things that could happen, to preferable outcomes, right? So those are things that we would want to have happen, that we're trying to actually sort of aim for. And you'll notice there's a little dotted line there. And of course, there's possible outcomes, right? So we'll come back to this and see why it's important in a second. But the other point I want to make is you'll notice that those circles, right, get bigger as time proceeds in the future. The range of those options increases as time gets further into the future. The possibilities, in a sense, get bigger, get wider. The other thing that I'll point out is the model. When they talk about this, they often use a flashlight model because it's informed by our cognition. In other words, where are we focusing our attention? So we can do this intentionally if we all sit down and done strategic planning for a quarter or for a sprint. We're doing this and we're purposely shining the light. We can also do this reactively. This is an incident response. It's where something has gotten our attention. We weren't meaning to pay attention to it, but it's grabbed our attention and we need to pay attention to it. We shine this flashlight around in the same way, whether we're intentionally doing it or we've been interrupted. So how does this relate to storytelling? I want to give a non-incident example. So if you go to a Starbucks, we all have a certain set of expectations about what is going to happen in that Starbucks. When I go in, I'm going to order a cup of coffee. I have a set of expectations about what's going to happen. If I see a person in a nice suit with a briefcase in front of me and they say, the person says, what do you have? What would you like? And they say, I'll have a bacon cheeseburger and fries. That would be an example of where the story broke down, where our sense of what's probable and plausible, and now we're off the line of possibility. I mean, it is possible, it just happened, but that's very odd. So the key point here is it's where the story broke down, and this becomes really important because we actually rely on stories in our day-to-day life all the time to reduce cognitive burden. That's why, we're not always on the prowl when we go into a Starbucks for, a lion to eat us, because that's probably not going to happen. So it's actually a technique that our brain just uses to reduce cognitive stress. Now, there's an interesting thing here. If that happened, the barista and that person might try to repair this story. They might say, well, this isn't a McDonald's, and they might try to figure each other out. One of the interesting things, especially from an incident retrospective perspective, as a thought experiment, if you were an observer and you saw this, what would you do if the barista said, okay, and took his money? There would be a story that we would have to figure out in our heads that we may not even have the help with those two people to figure it out. So that's kind of interesting. All right, now we're going to talk about the root cause of stress in incidents. There's only one cause of stress in incidents. You know me, I've real big on Twitter about the fact that there is only one cause to incidents. There is a root cause. And so we're going to find out what the root cause is. And actually, I get to put this slide in there because it is April Fool's. In fact, if you know me, I make a big deal about how root cause is not actually a thing. And my safety science nerd friends do as well. So to that point, there are obvious other causes of stress in incidents. And as do solutions, right? Drills training is a solution space to get better. Incident run book checklist I'm sure we've talked about those. And then mindfulness and breathing, right? So these are some solutions to stress in an incident. But I want to talk actually about cognitive stress. That's the thing that we're talking about today. So the biggest cause of cognitive stress in incidents is the fact that the stories that we tell each other about the system, the socio-technical system in which we exist, become not true or are no longer coherent. That is the biggest cause of stress because we've walked into that Starbucks and somebody's ordering a burger and it just throws us off, right? So let's go back to this slide and sort of contextualize that, right? So we expect the system to be in this preferable state. We hope that the system, the system might actually be in a probable or plausible state, right, when we walk up to an incident, but it's actually over here and in fact, we all know this, the worst incidents are way off in some possible thing we haven't really even imagined, right? And you can notice, right, the incidents, the complexity, if you will, of them cognitively is how far out of those circles the system actually is. If it's in a plausible area, it might be easier for us to fix the issue. So I want to talk a little bit about mental models. This is from Adaptive Capacity Labs, above the line and below the line. So below the line is where all our systems actually are, the computers and the code and all of that stuff, right? And above the line are the people. And you'll notice that people are talking to each other, and they all have their own ideas about how the system works. They're also slightly different. So what I'm talking about here is in incidents, these two things, how people think the system works and the way the system is actually working, no longer match. Also, during incidents, the coordination to figure out not only the differences in our mental models with each other, but also the differences in our mental models to the system. That's why there's a lot of coordination cost in that, and that's a cognitive burden, and that's why it's stressful. I want to talk a little bit about expertise because we'll come back to it. This is a paper called Seeing the Invisible Cognitive Aspects of Expertise. And so I want to talk a little bit about the elements of expertise because we'll come back to when we look at like the stories that we tell. So the difference between novice and experts is experts use their knowledge base to recognize typicality. What that means is they can recognize typical situations and situations that are not typical. They can make fine discrimination, so they can fine-tune things to get the outcome they want. And they can use mental simulation. Last one's really important in incident response because what that means is not only can they use mental simulation to figure out how the incident unfolded, like how did we get here, but they can also use mental simulation to look at the possible sort of outcomes. And so an example is when a set of firefighters roll up because of their experience, they can look at a fire and have some sense of how it started, and also based on their experience and expertise, know how they're going to put it out with the quickest and with the best outcome. Now, the interesting thing here is experts and expertise is the application of higher order rules. And the really interesting thing about this research is that it's not that novices can't apply higher order rules. The difference between experts and novices is that experts have a larger knowledge base. They have, in effect, more experience. So they have more experience to draw from. And as novices get more experience, they will use the same type of skills. So this mental simulation part, in fact, that's the next slide, an incident shortens the time that we can predict into the future. And so a junior engineer responding to an incident, because they may not have built out better mental simulation models. And by the way, any new SRE engineer that's new to a team, same issue, because they don't have experience with the system. They're going to sort of be obscured about how far out they can predict into the future. And that is why it is stressful. And so the thing that I would say to you is only when we can start to effectively project into the future again do we feel less stress. Only when we make a prediction and then it becomes true as we're trying to fix the system, that's when the stress of the incident response goes down. So I'm going to show you an example of that. This is a video. I want you to pay attention to kind of your feelings and notice your feelings as this clip's, I think, about 20 seconds. And notice when you feel those feelings. I'm going to ask you a couple of questions for you all to reflect upon after this video. So let's go ahead and watch it. And one of the things I'll ask you to notice is, when do you notice something doesn't look right with this plane? Now, the other thing that I'll ask you to notice, did you notice that the suspense or the stress that you might have felt when you watched this ended when you could reasonably tell what the rest of the story was going to be like, even though the incident is clearly not over? Did you notice any change in a lot of people sigh when the plane touches down to the highway? And you're kind of like, okay, everybody's going to be safe. Clearly, the plane should not be on a highway, so we still have some problems to solve. But we can project that out into the future that those people are going to be okay reasonably confidently, and the stress went away. So that's what I'm talking about. All right, how do we tell less stressful stories in the context of an incident and after? How do we reduce that cognitive stress during incidents? One way to do this, we talk about this a lot in the safety sciences, is to practice interpredictability. What is interpredictability? It has a number of components. Basic compact is one of them. Compact exists among the group. So what is the goal, right? What are we here to do? This can actually be kind of hard when forming an incident response group. As an example, developers may not see what the agreement of the compact is the same as operations people. And so that's something that's important to sort of make sure that you're aligned on. And you can do that outside of the incident, but there needs to be a basic compact. Goal alignment and commitment, it's related to that. For example, sometimes one of the things we say at Netflix is, as we're doing incident response, our biggest goal is to get customers back to happy. We are not interested in any sort of root cause analysis or root causing, you'll hear it sometimes. We're not really trying to figure out all the details of the system, just enough to get customers back to happy. Interpredictability, right? That is the skill of a team to be able to relate to and predict what other folks are going to do. So this is kind of a joke you'll see sometimes in pop culture where people finish each other's sentences, or really good friends finish each other's thoughts. That is an example of interpredictability. And so the biggest thing where you see this sort of violated in incident response is somebody will leave without actually letting the group know that they're not there. That's a lack of interpredictability. And then sustain and repair. It's similar to this idea that highly interpredictable groups actually are able to detect when their interpredictability has gone down and repair it. And there's a number of techniques to do that as well. Learning to move through time, also very important. I do not mean this. I don't mean Back to the Future. What I mean is, as you look in an incident at this cone of possible futures, it's useful to be able to look at those different circles, right? So what are the predictions and stories that I can tell in 10 minutes about the system that are probable or plausible versus stories that I might tell in a half hour that are probable and plausible? And the important point here is that a good incident commander is able to shift through these time frames to get a better sense of how the incident is unfolding. Are the stories that they are telling themselves in their heads and others as they are managing the incident coherent, and are their predictions correct? And that actually gives a sense of how the incident is unfolding. And the better, if you have somebody paying attention to this, it can reduce the stress because they're paying attention to these different time frames in which the possibilities are unfolding. During incidents, this coordination is, as I said earlier, costly and therefore stressful. So having somebody that is paying attention to that, again, the incident commander is super important. A lot of people often say in an incident, we all have to get on the same page. You actually don't want people in an incident on the same page, but you do want them reading the same book. And that's this idea that you're exploring those different possibilities, right? Maybe the database person is doing their part and the network person's doing their part, but you do want them reading the same incident book, as it were, but they don't need to be on the same page. And finally, structural support for adaptive capacity. What do we mean by adaptive capacity? So one of the things that you can do that's important is getting a sense of your team's current capacity for adaptation. I note this because COVID has impacted this in a huge way. But even before COVID, if you're running your team at 100%, then you probably don't have much rebound. You don't have much elasticity, and you don't have a lot of capacity to adapt to systems. This is where you see people getting burnout on on-call shifts and things like that. Do you have, understanding the degrees of freedom and the constraints in your system? So do you have structural constraints that limit your degrees of freedom in an incident? An example might be security or systems that you can't touch. It's important to we saw this with the Facebook outage, right? Where I think the thing was they couldn't actually physically get into the building because that was a constraint to solve whatever the problem was, right? So can you revisit those constraints, or can you make sure that as part of the standard process that you have, there's at least a representative from security that's pulled into incidents to represent, that constraint and help with the incident response team. Finally, deliberately creating space to share more stories, especially the incoherent ones. So this is effectively incident reviews, right? But it's worth talking about questions like, why did the site stay up? Or near misses, right? Or adaptive behaviors. The best stories in an incident review, and I know you all know this, are the ones where somebody says, I thought this was going on. Somebody else says, I thought this was going on. And then somebody brings some logs or something, and they were like, well, you're both about 40% right, and this is what's going on. That's not so much about correcting the record, as it were. That's important. But it's actually making the incoherent stories more coherent. And in a way that allows us to improve sort of our inner predictability between each other, because we can start to understand how others understand the system and how they might understand it differently than we do. And then we can leverage that either by helping them understand or leaning on them because we know they understand something. So the actual incoherent parts of a story about an incident are super important. All right, so what now? We're going to put all this together. What are the takeaways from all of this? All of this storytelling and all of these R words. Cognitive stress in incident occurs because our stories have broken down and the stories need to be rebuilt in real time. This is super difficult, and this is why it's stressful. This is why incidents are often stressful. Incident commanders can help the group effectively accomplish this task. And if you are an incident commander, one of the things that you should be really focused on and sharing as much as you can as you're managing the incident is, what is the current story that's going on about the incident? How can I shift through those time frames to understand, are the predictions that I'm making and that the others making, are they coming true so that I know that we're getting a handle on the incident? And if they're not, am I sharing that information with others that so-and-so tried something and it didn't work? So we're kind of back to square one. So this is hugely beneficial. And again, it's weird. It's all about storytelling. But so leverage that. The skills needed to make stories correct, and mental models coherent again can be practiced, and therefore you can improve them. So this is going back to that adaptive capacity and the coping mechanisms in your actual people that are doing incident response. So you can foster those, and you should. Practice team interpredictability and practice it, right? Get better at it. And there are a number of ways you can do that. But interpredictability is super important in emergent spaces like incident response and incidents. And finally, take note of your team's adaptive capacity. This is especially a big question as we all come back, as we all come off of the COVID low. Figuring this out is super important, and we need to actually nurture it. That's an active thing that we'll need to do, but you can't do this during an incident. So you need to actually do it outside of when we're all called upon and the pager rings to respond to when our systems and stories become incoherent. So be safe, be healthy, be resilient. Welcome back to the new normal, and keep in touch about all your applied resilience techniques. I'm J. Paul Reed on Twitter. That's all I got.